Okay, boys, we're going to look at proof by contradiction today. So let's get started. Now, proof by contradiction works by taking an assumption that the direct opposite of a statement or negation is true, and then showing by a logical argument that the assumption is false. Now, this is one of my favorite methods of proof, and this paragraph will make sense when we do an example. So here I've got to prove that root 3 is irrational by contradiction. So the whole idea is I don't prove root 3 is irrational directly. What I do is I suppose that root 3 is rational, right? And then from that, if you like, false assumption, I arrive at a false conclusion, right? And because my conclusion is false, that means my assumption was false. That means the opposite of the false assumption is correct. So let's see how this works. All right, so first of all, we're going to start off by saying suppose the opposite is true. So suppose that root 3, so this is the easy part if you like. Suppose root 3 is rational. Okay, that's our assumption at the beginning. And we're hoping to arrive at a false conclusion. Now what that means is if root 3 is rational, that means it's equal to, it can be written as a fraction, P over Q or A over B, where P and Q are elements of the integers. You have to be more specific though, right? And Q cannot be 0, obviously, because that means you get a 0 denominator. And P and Q have no common factors, okay? And P, Q have no common factors. Right, and that simply means that P and Q, that the fraction P over Q is the simplest possible fraction using the numbers P and Q. Now, if you really want to go crazy on the symbols here, we could say there exists a P and Q, which are elements of the integers, and Q is not equal to 0, and P and Q have no common factors. Okay, so that's our starting statement. Okay, now, if root 3 equals P on Q, I'm going to square both sides. That's going to give me 3 is equal to P squared over Q squared. Okay. Now, what I can do then is write this as P squared is equal to 3Q squared. All right, just by rearranging. And then you could write P squared divided by 3 is equal to Q squared. Now, that's an important step because this says that P squared is divisible by 3 because Q squared is an integer, isn't it? Okay, so Q squared is an integer. Let me just check something. That's still working good. Q squared is an integer. So that means P squared is divisible by 3. Now, if P squared is divisible by 3, that means P is divisible by 3. Okay? So, therefore, P is divisible by 3. Right? Now, how does that happen? How can P be divisible by 3 if P squared is divisible by 3? Well, think about it. I'll put a little bit of explanation over here. P squared is just P times P, isn't it? Okay, so if that's equal to some integer q squared is an integer because q is an integer, that means 3 must go into p. Okay, if this simplifies to some integer, right, then 3 must go into p. So that means if p squared is divisible by 3, that means 3 must go into p. So p is divisible by 3. Well, if p is divisible by 3, what does that mean? That implies that p is a multiple of 3, doesn't it? P is a multiple of 3. Now, if p is a multiple of 3, I can say, therefore, p is equal to 3k, where k is some integer. Okay? All right, so now we've got p equal to 3k. I'm going to sub that back into this. Okay, let's call this equation 1 if you like. So, therefore, 3k all squared, okay, is equal to 3q squared, isn't it? Okay, if you come back to here, I'm just subbing in 3k there. So that's going to give me 9k squared is equal to 3q squared. Okay, and that's going to give me, if I divide both sides by 3 now, 3k squared is equal to q squared. Okay, and then similarly, we could say, well, that means k squared is equal to q squared divided by 3. Okay, so that means q is divisible by 3, doesn't it? Because k squared is an integer, and if q squared is divisible by 3, that means q is divisible by 3. So therefore, q is divisible by 3. Right, now if q is divisible by 3, well, have a look at this. We've come to a contradiction, haven't we? Because p is a... sorry, that's not the one I wanted to circle. This one. This is what I wanted to circle. P is divisible by 3. Okay, so that's the key. We've just come to a contradiction because we said at the beginning that P and Q have no common factors. But if P is divisible by 3 and Q is divisible by 3, that means 3 must be a factor of P and Q, correct? So therefore, P and Q have a common factor of 3. Okay? But this is a contradiction, isn't it? Because we said originally that P and Q don't have common factors. So we'll say this is a contradiction. Right? So with contradiction, that means our original statement must have been false. Therefore, root 3 being rational is false. Okay, so I guess technically we should write that a bit better. It's not such good writing there. So let's say, therefore, the statement root 3 is rational is false, right? Which implies root 3 is irrational. Done. Okay, so just reviewing the proof there. So we started off with an assumption, suppose root 3 is rational. We had to define that using obviously the appropriate symbols, and making sure we say that P and Q have no common factors. We then work that through to get this equation, P squared equals 3Q squared. Right, now from that equation we can see that P is divisible by 3, because if P squared is divisible by 3, that means P is divisible by 3. That means P is a multiple of 3, so then we said P equals 3K, where K is some integer. And we sub that back into the original equation there that we had, and then we end up with something similar for Q. We end up here with Q squared being divisible by 3, which means Q is divisible by 3. Okay, because if you think back to the original statement, what does this mean? If Q times Q divided by 3 is some integer, that means 3 must go into Q. Okay, so if Q squared is divisible by 3, that means Q is divisible by 3. Okay, all right, so that means we proved that P and Q have a common factor of 3. This is a contradiction of our original assumption. Therefore, the statement root 3 is rational is false. Therefore, the opposite is true. That means root 3, the opposite to our original statement is true. That means root 3 is irrational. Okay, so let's try the same idea for this one. Use proof by contradiction to show that log of 3 base 2 is irrational. So what we're going to do is we're going to say, suppose, so you can pause the video now if you want to have a go at this one. Suppose that the log in base 2 of 3 is rational. Okay, therefore, log of 3 in base 2 is equal to P over Q. We could say such that there exists a P and a Q, which are elements of the integers. Q cannot be equal to 0, and P, comma Q have no common factors. Okay, now by definition then we're going to have 2 to the power of P on Q is equal to 3. Okay, now if we erase both sides of this equation to the power of Q, okay, we're going to end up with 2 to the P is equal to 3 to the Q, right? Now, 2 to the P is even, isn't it? Absolutely. And 3 to the Q is odd. You can't have an even number equal to an odd number, right? So therefore you can say that 2 to the P does not equal 3 to the Q. All right? So that being the case, that means our original statement must be false. Okay? So therefore, therefore the statement log 2 of 3 equal to P over Q I guess you should say that the statement that log 2 over 3 equals p over q is false, or log of 3 and base 2 is rational is false. Okay, so hang on, the statement therefore log 3 is irrational. Okay, so you've got to arrive at a contradiction. So here we found the contradiction here. 2 to the p is even and 3 to the q is odd. You can't have an odd equal to an even. So the statement log of 3 base 2 equals p over q is false. Therefore, log of 3 is irrational. Okay, sometimes at the end of these proofs they put QED, which is Latin, quod erat demonstratum, which means I proved what was required. Okay, so that's it for today.